We have Saso from Nexenta, and he has a combination of 2 or maybe 3 topics if he has time. So welcome. Thank you.
Thanks. Cool. Can people hear me? Awesome. So I'll be talking quickly about 2, potentially 3 features, depending on how much time we have available. I'm going to be try to be quick and leave most of the time open to questions. So first thing, or one of the big things we have been having trouble with is dedupe on basically any pool. Dedupe has a bit of a design flaw in that turning it on is really, really simple. You just set a property and you're done. And the problem is turning it off is really kind of hard, especially if the thing performs really poorly. So you turn it on, you write a bunch of data, you're happy going and trying everything out, and then you realize that, well, this thing is really just not performing at all. And so in frustration, you turn it off. Unfortunately, you then realize that as soon as you've written data, you still got to keep the buffers around, the dedupe table around, and that results in really, really bad performance. Even if you try to, even if you go the nuclear route and you just say, okay, I'm just going to destroy the data sets, and how long can that take? Well, if your dedupe hash table is out of memory, or most of it's out of memory, and you have to go back to some slow spinning disk or something, it'll result in really poor even delete performance. So you've basically gotten yourself into a really bad position, and it's a very hard thing to get out of that. And what's worse is that when you think about extensions, and all right, how could we sort of select portions of the dedupe table, your problem child, only to care about, well, like the really hard parts? The problem is it's a hash table. It's pretty much uniformly distributed. There's no really preferential portions of it that you're going to hit. It's basically a completely random read workload, even when you're trying to do relatively simple things. So even if you're thinking like you're writing just a linear segment, you're still going to get random reads into the hash table. So that really, really sucks when you're out of memory. So we thought to ourselves, like, so the primary design problems that we have considered is that dedupe really loves memory. It really needs a lot of memory to work, but it doesn't really care if it has it. If your dedupe table grows to 10 times your memory size, so what? It's your problem. You should have planned ahead, right? So the usual advice that we give to customers and basically give to anybody is like, how much memory you need. You got to consider that first. Then you got to consider what happens when I reboot, when I'm going to have a cold cache. Obviously, performance is going to suck. And can I get away with just a little bit less cache? Like, what happens if it just starts to overflow a little bit? And the answer is, yeah, you really can't get away with it much at all. And your performance is going to go down significantly as soon as that happens. So we have a problem where the problem can manifest itself almost completely out of your control unless you're really, really careful. And there's no easy way to back out of that. So we thought to ourselves, like, what if we just perform sort of the basic checks for you, so we don't actually let that kind of bad situation happen to you? We know the size of the dedupe table on your system, and so if your dedupe table grows too large, usually what you prefer is, I'm willing to just sacrifice a little bit of dedupe ratio for performance. That's usually how it goes. So we'll just stop adding entries when it grows too large. And we also what we did is we keep the dedupe table buffers in ARC segregated into sort of a different set of lists. That way we are able to provide more fine-grained size control for that. So we're actually able to tell you how much of your ARC is actually taken up by DDT, how much of it isn't. And you're able to then monitor your progress on that basically by either looking at some stats, looking at case stats of the ARC, or we'll even generate something like a dedupe on-off sys event, where you can basically just read a property. You'll figure out pretty quickly whether you are capped on RAM or capped on any kind of performance variable there from achieving a higher dedupe ratio. It no longer manifests as a sort of surprise, like suddenly performance is tanked. Why? And then you start going through all the entrails of ZFS, and you figure out, well, yeah, we've run out of caching space for the DDT, and yeah, could you please get us an additional 512 gigs of RAM, please? So we, I don't really have very good benchmarks available. I'm working from some older slides, so we have been working on, this is sort of the performance that we've been monitoring here, is where we simply let the dedupe size grow unconstrained, and then we just monitor latency for access. And obviously, when the thing sort of levels out on the right-hand side there, you can see that that latency no longer increases. It's actually not a very good data set, but this is pretty much what I had here. Anyway, so the second part of the deal here that we're trying to do with sort of fixing dedupe and getting some of this stuff into an actually usable state is the question that I posed, the second question I asked there. So we've resolved cache size. We need another thing, which is what happens when I reboot. Obviously, at this point, when you reboot, your caches are cold, and if you have several terabytes worth of L2ARC, yeah, it'll take a while for it to warm up. So, and this is especially problematic for dedupe, but it also applies to generally other data. So the design idea behind L2ARC is really simple. It's just keeping the L2ARC around. We facilitate that by just adding, sort of leaving little breadcrumbs in the L2ARC, just enough to let us reconstruct the buffers that have been stored on the data. Because usually when you're dealing with an L2ARC device, you're dealing with a device that is actually persistent, even though it didn't initially need to be. But so that means we still have the buffers on the device. We just need to find them. So we just leave little bits of pieces of metadata around. Usually the overhead for for persistent L2ARC is a lot less than 1%. And then on pool import, when we're adding the devices back in, we just quickly run through all the metadata entries that have been chained up on the L2ARC device and just re-add them back into ARC in sort of an evicted state. So basically, they're not in the ARC. We're not reading the actual data. We're just rebuilding the necessary headers to get to it. And of course, it's important for this thing to be not to impose too many format changes, so there aren't any format changes. Fortunately, because before this, L2ARC used to be non-persistent, so you would have been throwing it away anyways. So there's no format changes, and the rebuild happens in the background. So you're not going to piss off your HA guys who are trying to constrain the amount of time that you spent importing pools. So I have a small graph here that roughly explains it, hopefully. And what we do is we store a little device header on the L2ARC device itself that points us to sort of a doubly linked list. Well, not in two directions. It's more like two linked lists that are interleaved. That gives us the ability to do a little bit of prefetching. The reason for that is otherwise we'd be sort of doing it one step at a time, each time reading a buffer, decoding it, figuring out the next address we need to read, and going forward. And during this time, the L2ARC device would be sitting idle. So this speeds up the rebuilds a little bit. And the gray areas there in the middle, that's supposed to be like the actual data buffers that you have on the device. Each of these log blocks contains internal pointers over to the data buffers. And it's obviously not to scale, so the log blocks themselves will be a tiny, tiny, tiny percentage of the space on the L2ARC device. Most of it actually will be the gray areas where you have your actual data buffers. And so we hop over to the latest ones and just pass backwards through the list and rebuild all the L2ARC and ARC entries into an evicted state from that. Usually, the metadata overhead is about 1% of the space on the L2ARC device. It can vary, of course, if you have very, very small buffers, but it tends to be fairly small. So we've even made it a non-disableable feature, so it's just always on. We figure probably nobody's going to really care about losing 1% for the benefit of not having to worry about planning a week-long service downtime for when you reboot. The rebuilds happens in parallel on all devices. So when you import a pool, you have 20 cache devices, and we're going to punch out 20 threads. And it does not slow down pool import, so it happens in the background. That means if it took 20 seconds to import your pool before this, it'll still take only 20 seconds. In the meantime, we will be allowing reads to the new buffers that have been already rebuilt as the rebuild is progressing, but we won't allow writes to the devices as the rebuild is going on. Usually for a 500 gig L2ARC device, it takes fairly little time, so about 5 to 10 seconds is what a typical rebuild takes. It can vary. There are ways to constrain that. And if necessary, you can either disable the rebuild of a specific device just by removing it out of the pool, or it generally does not block even pool export. So if for whatever reason your rebuild is taking 5 minutes and you want to get rid of the pool anyways, just want to export and whatever, be done with it, it's just destroy it, export it, whatever. It does not block that. So it is interruptible. So how does that work in conjunction with the dedup, with the scalable dedup thing, is we've integrated a feature into ZFS that allows us to have per VDEV properties. So it basically behaves almost like a ZFS file system or dataset property, but it's set to be per device. And when you set that specific property for an L2ARC cache, it'll basically cap the size of the dedup table at the size of that cache. So you can sort of segregate out your cache devices. You have 5 caches, and you want to have 2 that are dedicated to your dedup tables. Set their type to DDT on those devices. We automatically figure out the maximum size of the DDT, and when you reach that size, we'll just tell you that dedup is currently turned off because you've reached maximum capacity. And since it's persistent, you don't have to worry about rebooting the thing. It'll be always cached on these devices as long as you either remove them or do whatever with them. So fundamentally, it hopefully makes it takes the hassle out of planning and worrying and nail biting, or not being able to sleep when you worry about there being too much data in your memory. The properties themselves are stored in the MOS, the aforementioned meta object set. So it's just a ZAP directory with that is linked to a particular device. They're not stored in VDEV labels or anything like that. In the future, we're working on extending the usefulness of these properties. It's not just for this one gimmick. It's meant for other much more interesting features. So we would be looking into constructing much more interesting topologies for devices and working on some nice features that really doesn't make sense to elaborate right now, but we can talk about that when we're during the break. So the fun part for me personally, one of the things that I did most recently, and that's going to be open source pretty soon, is going to be trim and unmap support in like the proper thing, the real deal. So what quickly run through the 5-second intro of what trim or unmap or discard is basically it's a way for the file system to talk to the underlying storage device and tell it whenever some blocks have been freed, we'll just notify the device, and the device can do whatever it wants with that. Usually this is used by devices like NAND flash devices to perform some sort of garbage collection. They can pre-erase blocks and just prepare them. It also means the practical upshot for our storage pool is that your sync write latency won't necessarily tank whenever you reach a fairly high fill rate on your device. Usually when you're talking about NAND flash, it performs really well as long as you have pre-erased blocks. And then when for whatever reason you reach like 80% of your capacity, NAND flash thinks like, oop, well, we're out of blocks right now, so whenever you now do a sync write, you got to wait for a new erase, and it just completely messes up. And problem is it wouldn't even go away. That kind of problem wouldn't even go away until when you reduce the amount of space used because the NAND flash device would still think that you're using that fairly high allocation. Before TrimUnmap support in ZFS, you would have to basically take the device out, do a secure erase, and stick it back in. So with this, we are able to sort of shrink our allocation on the device as you're deleting data in your regular course of action. Another thing that it's nice for is for either thin provision SAN or VMDKs, even on VMware, something like that, where we're able to give space back. So when you're running, your Illumos VMs on your storage array, you won't be eating up just chunks and chunks of data, even though your pool is practically empty. So that'll make your storage admin not hate you. So the general implementation that we have done, so the features, if you want to actually see the code, talk to me later, but the interesting features are that we are able to support any kind of pool geometry. It's implemented, well, basically at the very, very bottom of the SPA. It's basically living in the metaslab layer. So we are completely agnostic to the way the pool is laid out. We support any kind of leaf VDEF type. So you can either have the pool composed of files, you can have it composed of disks. And in each case, we are using the appropriate method of freeing space on it. I would hope to be spending my time tomorrow during the hackathon to make these Illumos-specific things sort of more general so that other platforms can more easily integrate them. We are able to then, of course, also auto-detect whether a hardware advertises support for a piece of hardware advertises support for TrimUnmap, and we are able to skip that hardware. So whenever we're doing a trim of the pool, we're not actually issuing trim commands to something like a spinning hard drive, because that doesn't make sense. That hard drive does not obviously support that. We skip extents that are too small, so usually 1 megabyte, that's the typical cutoff for most SSDs. But you can set it down to whatever number. If you wanted to, you can set it down to 0, and we'll trim every little piece of free space that we have, that we can see. And most importantly of all, it doesn't require any pool format modifications, so there's nothing, hopefully, that will make you have problems rolling back. So there's two ways you can invoke this feature. We have basically built in two methods of using trim on ZFS. The first feature is, we call that automatic trim. So you just set a property on a pool, set auto trim to on, and that's basically it. That's all you have to do. It's off by default, but what it does is it tracks allocations and frees in the metaslabs, and as data is being freed, it automatically prepares and sends out the trims while your regular transactions are being committed. So once it's enabled, you don't pretty much have to worry about it at all, and you can disable it if you want to. Finally, the trimming operation is, we try to make it progressive, or we try to make it roughly, we try not to pound on the devices too hard, so each transaction group, we sort of trim out portions of some metaslabs, and then sort of do another set, and the next one, and the next one, and the next one. It preserves the ability to recover from disasters, so in case you need to do a zpool import minus capital F, you can do that for between 34 and 66 transaction groups into the past. So otherwise, if we did it right away, it would basically, as soon as your blocks fell off the deferred list, you would not be able to recover them anymore. So that's the reason, and it also improves some aggregation. So rather than trim each 128K block individually as it's being trimmed out, as it's being freed by the upper layers, we automatically join up adjacent sections and send them out in bigger extents. It helps the devices cope with our command workload. And there's one problem with the automatic trim feature, is that some devices, when you're pretty high write workloads, when at that time you also try to give them some unmapping work, at that point the devices can get pretty unhappy with you, and your write performance can go down. It doesn't happen in each one, and it really depends on the specific firmware. sometimes even the specific revisions of firmware that you're running in those things. So it might not work all that well in these cases. And for those guys, we have designed a second way, which we have really creatively called manual trim. And what it does is it's just a batch operation that you run on your pool once through. It's meant for sort of batch processing or low usage hour processing. What it does is just runs once through all the free space on a pool and recovers everything, trims out everything. That's why I said it's kind of similar to the eager zeroing that the Delphix guys have been talking about, is because this basically does the same thing. The only difference is rather than issuing writes of zeros, we issue trim commands. It's executed in parallel on all top-level VDEVs, and it can either proceed at maximum rate or you can set a manual rate if you want to limit the impact. So I don't know, you want to have it trim at 4 gigs a second per device. That's what it'll do. It can be monitored, and either through human-readable interfaces like zpool status. You can watch for sys events on it. You can monitor it manually through libzfs in your own code. All of it works. In order to achieve maximum space recovery on this thing, we don't actually delay these trims, the extents that we trim out here for a little while. That means that immediately during the trim operation, this thing basically goes through all the free space regardless of how recently it was freed. So that means during the operation and just immediately following it, the disaster recovery through zpool import minus capital F might not be assured. So that might be a bit of a thing there. It was a design decision to enable maximum space recovery, but we could play around with that if need be. And yeah, it's as I said before, it's really meant for cases where you determine that automatic trim does not work for you, it impacts your workload or whatever. Then you can just run this thing once a night or something like that and reap most of the benefits of automatic trim with an additional little bit of work associated with having to run the thing in a cron job. So this is how it actually works. I'm going to use a pointer here. I'm going to actually do this. Oh, there we go. Cool. So this is sort of a side-on view of how the thing works in time. So here we have a time axis that flows from left to right. And these are sort of individual transaction groups as a sort of time representation. Initially, you start out with having an allocated region, and somebody frees out a location called DVA free, Metaslab DVA free. This happens, of course, after all of your snapshots and everything has figured out that a block is really meant to be freed. So what happens in your Metaslab is it gets added to a tree of freed locations that then right in the next transaction goes over to a deferred delete tree. That's by default on ZFS. That's 2 transactions long. So during this time, this is already existing in the existing code base. During this time, your freed block will not get allocated by anything else. This is sort of your existing grace period inside of ZFS. After these 2 transactions have elapsed, that block gets added back into the tree of free space. That's the main Metaslab tree. And after that, it's again available for new allocations. Now the new feature, the automatic trim feature, what it does is it also adds the block over to a new what we call trim set, but it's basically just another tree of extents. And in that, it is being aged out for a certain amount of time before it is eligible to be really discarded. At any point during this time while it's being aged out, you can get an allocation out of the main tree, and that automatically also pulls the extent away from the extents that are to be destroyed. So once a certain amount of time has passed, what we do then is we swap it over to from the current trim set, we swap it over to the previous trim set. And the previous trim set also sits idle for a little bit longer, for usually 32 transactions. So That's why I said that it takes between roughly 34 and 66 transactions. That's roughly double this time over here for an extent or in a given block to be considered to be really free, and that you're really not going to use it in the next little while, and that we've really gotten the best possible sort of adjacency aggregation on it that we can. And once that happens, after that sort of grace period has elapsed, we then grab the previous trim set, send it out to ZIO trim, throw that basically in the trash, take the current trim set that has already aggregated, again, some of the extents that have been freed in here, and then that becomes the new previous trim set, and open a new trim set. Basically, it's a way to make sure that any blocks that we're about to destroy have been sort of properly aged like good wine and are fit for consumption for ZIO trim. Now, this is sort of a side-on view, so everything I've been showing you has been happening in this portion over here. And now I'm going to talk about roughly how the commands go down to your devices. What we do is we issue ZIO trim to a particular device. These are represented as top-level devices over here. And that then depending on the actual VDEF type, either goes down to, if this is a straight-on disk, it'll just go straight down to the disk portion. But if usually you get a mirror here or a RAID Z, in a mirror we just duplicate out the ZIOs and send them to both the constituent VDEVs. In a RAID Z, we do a fake sort of a shim RAID Z map alloc, and we figure out exactly which extents need to be trimmed out on the component devices, send those away. For files, we just do an FCNTL for F3 underbar SP, and that goes down to your VFS layer and to whatever file system you're running this on. So you'll get file hole punching in these cases. On disk devices, we issue an ioctl, which in Illumos is DKOC free. That goes down to your block layer and hits your SCSI device driver. And on SCSI devices, it generates an unmap command, goes either to your SSDs or your SANs, or in the future, if somebody is masochist enough to write this piece of code to go to the SATA translation layer and goes out to a SATA SSD. But we currently haven't done that because that's not critical for us. So that's all I have for my part. If you have any questions, feel free to ask. Yeah, go ahead. Yep. Yeah. So this would make problems with rewriting data. Okay, I'm not sure I completely understood, but I think the question was whether we should be adding extents to the MS tree at all, whether we shouldn't just be going straight to the trim tree or trim set, and then once they've been trimmed out, then they get added back into the space of allocations that are available. So this would actually mess a little bit with your sort of in-place rewrites. It would inflate the amount of overhead that you have for an in-place rewrite. Usually at this point, when you have, say you're writing, I don't know, overwriting a gigabyte a second, and or a gigabyte a transaction, and you're overwriting in place existing data. What the old data happens is, of course, ZFS is copy on write. So the old extents or the old blocks get added to this defer mechanism. But since you're still overwriting in place, you have to realize that these guys, after they've been deferred out and gotten back into the MS tree, they're still available for allocations. So the beauty there is that you don't actually get too much overhead, too much sort of extension of this delay mechanism out into your trimming. The point of trimming is not really to make sure that every time you free a block, you just immediately get rid of it through trim. The point of trimming is to make sure that the aggregate space that the device underneath you thinks is being used is actually being used. When you're just reusing the same blocks over and over again, even though you're copy and write, you can still reuse them in a sort of a relatively short amount of time. That's fine with the device underneath. The problem only comes when you do a bunch of allocations, you've used that space for quite a while, and then you free a lot of it up, and you just forget about it, right? And you just keep on doing whatever your stuff is at the low allocation mark, and you just forget about everything up there. That's why the delay mechanism is in there, and that's why we allow reallocations from that region to make sure that stuff that we're about to trim is really something that hasn't been used in a while. If the pool wants to reuse the same block, we'll just let it have it. Yeah. Yeah. So the idea, MS3 is already free. We don't actually need to take stuff out of it. If at this point we're trimming, actually what we do is while the trim is ongoing, we don't actually allow allocations from the specific extents that are currently being trimmed. But before we issue the trims, we allow anybody to just grab them. Yeah, the point of these trim set trees is not to be like stuff that has been freed and we just quickly grabbed it away from user space. These are supposed to be like the really unused pieces of garbage that nobody really wants. Yeah, we're out of time.
Thank you for putting all